Hello students, we are going to see sinusoidal pulse width modulation. So why do we need this modulation technique? Earlier we have seen for a full bridge inverter, these are the switches S1, S2, S3 and S4. Okay, so to get the output as positive EDC, we are going to turn on S1, S2. Here T1, T2 stands for switches 1 and 2. To get negative peak of output, we are going to turn on S3, S4. So while S1, S2 are turned on, S3, S4 are turned off. Similarly, while S3, S4 are turned on, S1, S2 are turned off. So this was the scheme for getting AC output. But coming to AC output voltage expression we have, so that was V naught equal to summation 135 up to N 4 VDC pi N pi into sin omega t. So this was the expression for full bridge inverter, right? Single phase full bridge inverter. So coming to fundamental RMS, V01 RMS. So that was something like Vm by root 2, right? Vm was 4 VDC by 1 into pi because fundamental n equal to 1 into root. So this was the fundamental RMS output voltage. So if you observe here, can you change the fundamental RMS output voltage? So what I mean to say is this fundamental RMS can't be changed and it has dominant harmonics of the order 3rd, 5th and 7th. Okay, so we know what are harmonics. Harmonics are the frequencies other than fundamental frequencies superimposed on the signal. Okay, so we want the output for our inverter to be a sinusoidal waveform, but because of the presence of these harmonics here, okay, so the output is changed to a square waveform. So we know this, right? So but we want a sinusoidal output voltage, RMS output voltage, fundamental RMS voltage. Okay, so how can we get this fundamental RMS voltage as sinusoidal? Okay, so to make this happen, we are going to use this technique that is called pulse width modulation. Okay, so we know that the output voltage has dominant harmonics, okay, which are not desirable. Using PWM techniques, we can change the fundamental RMS voltage and we can try to eliminate the dominant harmonics from the output voltage. Okay, so this is what we are going to do. We are going to change the output voltage to be a sinusoidal waveform and we are going to eliminate these dominant harmonics which are 3rd, 5th and 7th. Okay, so we are not completely eliminating harmonics, but we are going to eliminate the dominant harmonics here. Okay, remember that. Now let us see what is pulse width modulation. Okay, pulse width modulation. Okay, so the short form for this one is PWM. Okay, so generally there are so many techniques. So few of them are single pulse width modulation, single PWM. Second one is multiple pulse width modulation. Okay, and the famous one we are going to talk about is sinusoidal pulse width modulation. Okay, so I hope you know what is a modulation. So modulation is nothing but we are going to superimpose a weak signal onto a strong signal and we are going to transfer or transport that signal just like an FM, right? So here we are going to have two waveforms. So one is a carrier waveform which has very high frequency, okay, in the order of 20 kilohertz. Okay, so this is a carrier waveform I am drawing here. Okay, so we are taking them as angular position and what we are going to do is we are going to superimpose any waveform like this is our carrier waveform and we are going to superimpose, if we superimpose a DC voltage, so this will be the DC voltage, reference voltage. So this one here is called reference voltage. So this reference voltage can be anything. Okay, it can be a DC voltage, it can be a sinusoidal waveform. Okay, so for example I am considering DC waveform, for example. Okay, so here you can see here. So when the reference voltage, this is VR, let us take this as VR, and the carrier voltage as VC. So here carrier is DC triangular waveform and reference is DC waveform. Okay, so let us say plus VDC and here it is minus VDC. Okay, so if you clearly observe this, when VR, the reference voltage is greater than VC carrier voltage, we are going to get a pulse here. Actually these two waveforms will be sent into a comparator, will be compared by a comparator. It can be op-amp based or diode based. Okay, so here we are giving the input for comparator as reference voltage and carrier voltage. Okay, so this comparator will give the output, the pulse. Okay, so the pulse when VR greater than VC, when reference voltage is greater than carrier voltage. Here you can see the black colored waveform is carrier waveform, and here we have a DC reference waveform. Here you can see this one here. This is DC reference waveform. Right, so this is DC reference waveform. I have changed the color to pink here to understand better. For better understand, I have changed the color to pink here. So the pink color waveform is reference waveform, which is DC here, and carrier waveform is a triangular waveform. Okay, so generally the frequency for carrier waveform is very high, in order of 20 kilohertz practically. So to understand it clearly, we have reduced the carrier frequency to around 6 hertz, right? So here we have 3 pulses for 1/2 cycle. So for one full cycle we are getting 6 pulses. That's why the frequency is 6 here. Okay, so if you observe here, we are getting a pulse when the reference voltage value is greater than the carrier voltage. Here you can see the black color one is less in this region compared to pink color one. Okay, that means VR is greater than VC in this region and we are getting a pulse here. Similarly here also. So we are getting 3 pulses in 1/2 cycle, either in positive or in negative half cycle. Okay, so if we consider the average of these pulses here, we are going to get more or less a sinusoidal waveform. If we try to evaluate the average of these pulses here, we are going to get a sinusoidal output. So this is what we need as fundamental RMS, right? A sinusoidal signal, right? So if we find the average of these pulses, we are going to get more or less a sinusoidal output waveform. So this is why we are going to use pulse width modulation. Earlier we had one pulse for 180 degrees and we had order of harmonics as third, fifth, seventh. Now we have somehow reduced the pulse using the pulse width modulation and we have managed to get the output as a sinusoidal waveform. Okay, so this is the advantage of pulse width modulation. This is about multiple pulse width modulation. Okay, with single pulse, that will be single pulse width modulation. Okay, here if you observe here, this is the pulse width here. Okay, so let me write down here. Okay, pulse width. Okay, so which equal to, generally pulse width is given as 2D. Okay, and we have n number of pulses in 1/2 cycle. Okay, n is the number of pulses in 1/2 cycle or per half cycle into number of each pulse into each pulse. Okay, so this is the pulse width. Actually pulse width 2D equal to number of pulses per half cycle into each pulse. Okay, so I hope you understand. Okay, now what we are going to do is we are going to get the fundamental RMS V01 equal to, if we find the RMS, that will be VDC into 2D by pi here. That means we can change the pulse width so that we can change the fundamental RMS voltage. Okay, so here all these pulses in 1/2 cycle will be having a pulse width of 2D actually. Okay, so the sum of each pulse will be having 2D by 3. So the addition of 2D by 3 for 3 pulses will give us 2D here. Okay, that's why we have 2D as pulse width in 1/2 cycle. This n is 3 here, into each pulse has 2D by 3. So that will be equal to 2D here. Okay, I hope there is no confusion here. So using these pulses we are going to get the fundamental RMS as VDC into under root 2D by pi here, okay, where 2D is the pulse width. Okay, so now we are going to define the number of half cycles per number of pulses per one half cycle. Okay, so number of pulses per one half cycle. So if we consider this waveform here, so how many pulses are there? There are 3 pulses, right? Okay, so there are 3 pulses. This is generally given as number of half cycles per number of pulses per half cycle. Okay, now if you observe here, so here this is the time period Tc when Vr is greater than Vc, and there are 3 such periods here. Okay, so that means we have 3 Tc here in one half cycle. So what is one half? So one half cycle is this one. This is total cycle Tr here, reference waveform, and here this is Tr by 2, one half cycle. So in one half cycle Tr by 2 period there are 3 Tc here. Okay, that means I can write 3 Tc is equal to Tr by 2. So coming to Tc, this is time period for carrier waveform, which is equal to 1 by Fc, right? Similarly, Tr is time period for reference frequency, that is 1 by Fr. Okay, if I substitute these two values, that will be 3 into Tc is 1 by Fc. Similarly, Tr is 1 by Fr, 2 into Fr. Okay, here the number of pulses are 3 here, that can be replaced with n here, right? 3 can be replaced with n, and I am going to shift this Fc to here, that will be Fc by 2 Fr. So this is the expression for number of pulses per one half cycle. Okay, I hope you are getting it, right? We have derived the expression for number of pulses per half cycle, and we denote it with n equal to Fc by 2 Fr. Okay, so this is important factor here. Now what we are going to do is we are going to know about a sinusoidal pulse width modulation. Earlier we have seen the reference voltage was DC voltage. Now we are going to use a sinusoidal waveform as reference waveform. Okay, so here I am going to define few things here. So here Fc is carrier frequency. Generally it has a 20 kilohertz order, okay, which is very much higher compared to our reference wave frequency. Fr is reference frequency. Wave frequency. Generally for sinusoidal we use 50 Hz because we want the output voltage to be 50 Hz sinusoidal waveform. So we are using reference frequency as 50 Hz. This can also be called as modulated waveform. Okay, so what we are going to do is we are going to get the output voltage V01 RMS, okay, as sinusoidal waveform using this modulated waveform. Okay, the more near the sinus, so the output voltage will be nearly equal to reference waveform here. If we apply a reference waveform as sinusoidal, the output voltage will be following the reference waveform only, that means sinusoidal waveform. Okay, I hope you understand. Okay, so we are getting the fundamental RMS waveform nearly equal to sinusoidal waveform because we are using a sinusoidal reference waveform here. Okay, that is one thing happening, and one more thing is we are changing the harmonics, order of harmonics to the multiples of carrier frequency. If you observe here, earlier we had 5th, 7th and 5th, 3rd, 5th, 7th as higher order harmonics without PWM technique. Now we are using a PWM technique. What happening here is the order of harmonics of the output waveform will be shifted to around 9th to 10th, 9th, 11th like this, 13th like this. Okay, so the dominant harmonics were 3rd, 5th, 7th earlier, but now they are 9th, 11th and 13th. Okay, so we are going to prove this. Okay, so the dominant harmonics with PWM technique are 9th, 11th 13th, which have very less magnitude compared to your 3rd, 5th and 7th harmonics, and these higher order harmonics can be easily eliminated using external filter circuits. Okay, so the complexity of filter circuits is reduced, okay, using PWM technique, because to eliminate 3rd, 5th and 7th harmonics, the filter circuit needs to be very complex. Okay, so using PWM we are changing the dominant harmonics to 9th, 11th and 13th, which can be easily filtered out using a normal filter circuits. Okay, so by using PWM technique we are getting the fundamental RMS nearly equal to sinusoidal waveform, and we are eliminating the dominant harmonics 3rd, 5th, 7th, and we are shifting the dominant harmonics to 9th, 11th, 13th, which can be filtered out using external filter circuits. So this is what going to be happen now. Okay, I hope you understand. Now we are going to see the pulse width modulation for sinusoidal reference waveform. So here you can observe this. We are having a carrier waveform as triangular waveform. Okay, so here carrier wave is triangular, which is generally having the frequency of 20 kilohertz. Okay, very high frequency, and we are having the reference or modulated signal as sinusoidal. That's why it is called sinusoidal pulse width modulation. Okay, so if you observe here, whenever the reference voltage, which is sinusoidal voltage, instantaneous value greater than the carrier voltage Vc, we are getting a pulse here. Okay, so if you can observe here, so this is a period when Vr is greater than Vc. You can see the green color one is a sinusoidal waveform which is having one full cycle in the given time period. Okay, so this is having one full cycle in the given time period, so t here. So if you want to write the frequency of this reference wave, that is one hertz in the given waveform. So coming to the frequency of carrier waveform, here we are getting 3 pulses. Okay, so like actually 3 pulses for 1/2 cycle, so that will be 3 hertz. Okay, so for total full time period it is having 6 hertz, 6 cycles, right? So if you observe here, carrier frequency is higher compared to reference frequency. Okay, now if you observe here, whenever Vr is greater than Vc, we are getting a pulse here. Okay, so here, and you can see that the width of each pulse is different. Okay, the pulse width is different. Width of each pulse is different here. Okay, so this is sinusoidal pulse width modulation, and what we are going to get is, so if we somehow try to find the average value of this output waveform here, the pulses here, we are going to get a nearly sinusoidal waveform here, like this. Okay, I am going to show you that. So if you observe here, this is the practical pulse width modulation using sinusoidal waveform. Okay, so you can see the brown color ones are pulses which are being generated by sinusoidal pulse width modulation, and we have obtained the average values of these pulses, and we obtained that it is nearly equal to sinusoidal. You can see that. So the brown color were PWM pulses, and we have found the average of these pulses, and we have obtained a sine waveform. This is the output of inverter fundamental RMS output using PWM technique, which is sinusoidal PWM technique. Okay, I hope you understand now. So we are going to get the fundamental RMS waveform, which is almost equal to a sinusoidal waveform, and we are going to get the harmonics. So coming to harmonics here, we need to find one factor that is called modulation index. Okay, given as indicated with small m here. Okay, so modulation index is defined as the ratio of reference peak voltage of reference waveform and peak value of carrier waveform. Okay, so generally the modulation index is ranging from 0 to 1, that is less than 1. Okay, so here using this modulation index we are going to get the order of harmonics, which is given by 2 into Fc by 2Fr plus or minus 1 here. Okay, so this is the order of harmonics. So Fc by Fr is nothing but number of pulses per half cycle, right? This is the expression we have. So I am going to substitute this as 2n plus or minus 1 here. Okay, so in the given waveform here, so how many pulses are there here? There are 6 pulses, right? One for one half cycle. So here we are having 3 pulses for one half cycle, right? So 1, 2, 3 here. For one half cycle we have 3 pulses. So n value is 3. So I am going to substitute that one into 2 into 3 plus or minus 1. So that means 6 plus or minus 1. So this can be 5 or 7 here. Okay, so the order of harmonics now are 5th and 7th. Earlier it was 3rd, 5th and 7th. That means we have eliminated the 3rd order harmonics, which is a dominant order harmonics. Okay, so for a small example here, we have eliminated a 3rd order harmonics. So practically there will be n value will be around 50 to 100. Okay, that means there will be 50 pulses per one half cycle. So what will be the order of harmonics then? Order of harmonics, which is given by 2n plus or minus 1. So for n equal to 50, what is its value? That is 2 into 50 plus or minus 1, that is around 100 plus or minus 1, that is 99, 101. So here you can see, so the dominant harmonics without PWM were 3rd, 5th and 7th, which are having very high magnitudes. Okay, so that are deteriorating the shape of the output waveform. Now these harmonics, the dominant harmonics are shifted to 99th and 101. Okay, that means in one full cycle they, so if later consider this is time period here t. So in one full cycles there are 99 cycles. That means what is the magnitude of that one here? That means very small one. That means we can almost get the fundamental RMS voltage, okay, almost equal to a sinusoidal waveform, because the harmonics are very higher order harmonics which are having very less magnitude, sinusoidal waveform. So by using PWM technique we have eliminated the dominant harmonics. We didn't eliminate, we have shifted the dominant harmonics to very higher order harmonics. So these higher order harmonics can be easily, eliminated or filtered out using filter circuits. Okay, so these filter circuits may not be a complex one, these will be very simple circuits. This will also reduce the cost of the filters. Okay, so this is about sinusoidal pulse width modulation. So the entire aim of the sinusoidal pulse width modulation is to change the higher order harmonics from dominant harmonics to very higher order harmonics which are having very less magnitude. Okay, and to make the fundamental output RMS voltage almost equal to a sinusoidal waveform. Okay, so this is about sinusoidal pulse width modulation. I hope you understand. Thank you.